Okay, so just to check everybody can hear me and see my slides.
Yep.
Okay, awesome. So thank you for the introduction. Yeah, so my name is Simone Hagey. I'm a master's student at the University of British Columbia in Canada at the moment, but I'll be starting my PhD in the fall here as well. So I'll be continuing all of this work and I'll be in the same location and everything for contacting. My supervisor is Erin Boley on the far right there. And we are also working with Billy Edwards, who, yes, is very involved in the Exoplanet project. And he is currently at the CEA in Paris. So I'm super excited that I get to talk to you all about my research. The timing could not have worked out better. It's like, it just feels very serendipitous that we're finally reaching the end of this project. And then I get the opportunity to speak to all of you. It's really wonderful. So the purpose of this project, the purpose of my master's thesis in general was to search for long-term variation in the orbital periods of ultra-short period hot Jupiters. So what we're doing is looking for transit timing variations, but those that occur over very long time scales and aren't necessarily periodic and can be evidence of phenomena like orbital decay or apsidal precession, which I'll talk about in a moment. But what it all boils down to is what does the future evolution of these types of planetary systems look like? And then what naturally came from that is the other half of this project is demonstrating the impact that citizen science data can have on understanding this type of long-term evolution. So I wasn't sure how big the audience would be today. I wasn't sure what range of backgrounds we have. So I wanted to cover some background information that might just be trivial to some of you. So I apologize if it's just review, but I wanted us to all be on the same page. So the data that I'm working with is just the transit center times themselves. So for this project, we weren't even looking to refit light curves because it was meant to be, as I'll explain in a bit, meant to be an efficient review of resources to search for nonlinear timing trends. So we just took transit center times at face value. So any given transit center time, as you know, for a planet on a fixed, unchanging orbit can be easily predicted by this linear law, very straightforward. You have some reference transit time, whatever epoch you've decided is 0 for your case, and then you just add however many periods have elapsed since that reference transit time. So any transit time is predictable it grows linearly, and any deviation from this linearity is what we call the transit timing variations. And as you've already seen even this morning, or it's morning for me, I know it's not morning for everyone, but we study these with these OC plots, observed minus calculated, where we subtract that linear trend and look at the timing residuals that remain. So one of the most common applications of this technique right now is studying multi-planet systems, because if you have multiple planets in a system, they can tug on the transiting planet gravitationally and cause these periodic transit timing variations. But as I told you, I'm more interested in these systems where you have a massive gas giant planet orbiting very, very close to the host star, because then what we're looking at is tidal forces interacting between the planet and the star that can cause something called tidal orbital decay, where the orbit of the hot Jupiter will shrink over time until eventually it's fully engulfed. So the mechanism behind this is a transfer of angular momentum from the planet to the star through misaligned tidal bulges. I won't get too much into that at the moment, but what you have here is a description of this process. You have a constant change in the period. This current model has a constant period derivative as the planet's orbit shrinks. And it depends on what you would expect, your mass ratios, your stellar radius, semi-major axis, but what it also depends on is this stellar tidal quality factor, Q. And this is something that we cannot constrain observationally at this point. So if we were able to measure this dp/dt, this period derivative, we could actually finally constrain this quality factor and learn more about the detailed dynamics of the system, and the interaction between the decay rate is not just cool because the planet's decaying, which is, I mean, that's cool, that's why I got into it, but it also, so what is that actually, oh yes, I had this slide. So we want to measure the decay rate. So how do we actually do that? So as I told you before, we have this simple linear law for an unchanging orbit. And so if we have orbital decay, we introduce this quadratic term with, again, that constant period derivative. Now here I've written it as dp/dE, the change in period per epoch, but it is a simple transform back to dp/dt. So just a different form of that. And it is negative because our period is shrinking over time. And so what this animation was intended to show you is that as the period shrinks, the planet sort of pulls out in front of where it would be in an unchanging orbit. And so the transits start happening increasingly early. And as I told you before, and so in this case, all we're left means is that the decay of the orbital transit timing variation. And this, and I will have, there is, I'm sure many of you know, there's one planet that has been indisputably confirmed to be decaying, WASP-12b. And this is a plot from one of the first papers to talk about this discovery, Patra et al. In 2017. And he also worked with Josh Wynn, who one of his other students is here today, and she's going to be talking about their paper that they recently did of test transit timing of hundreds of hot Jupiters. And that is an absolutely fantastic paper, and a lot of work went into that. So I highly suggest you read that, because the kind of work that I'm doing here is going to depend very heavily on all of the hard work that goes into getting these baselines to look at. So, so this is what the data actually looks like. You can see in the transit timing residuals, you can see that beautiful quadratic trend there, that parabolic curve. The decay rate of WASP-12 is about 30 milliseconds per year, which doesn't sound like a lot, but it actually really does add up over time. Now what you might notice is that something you could do is you could actually draw a sort of a sinusoidal curve on top of this and say, hey, are we actually looking at a decay? Are we looking at something that will keep going down? Or could we actually just happen to be looking at the peak of a sinusoid and it will eventually come back up? And so that's what these green lines here are indicating. And we have to consider that because this is a phenomenon that actually could happen. And it's called apsidal precession. So I have the timing model up here, but I won't dig into that too much. What happens if you have an eccentric orbit, even just very slightly eccentric, you can have this precession where the line that connects the periapse and the apoapse of the orbit will start to rotate over time. And so it's a steady increase of the argument of pericenter. And this is something that will repeat just on very, 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 very long timescales. And so because the planet moves faster at peri and slower at apo, for half of the precession period, your transits will come a bit early. And for the other half of the precession period, they will come a bit late. And that is why we need to look at the possibility of something that would be curving like what we see in our data, but that would come back up eventually because it actually maybe is this apsidal precession. Now, I'm introducing this as though it's some sort of nuisance thing, but actually apsidal precession is inherently very interesting in its own right. If we were to measure a precession rate, it would allow us to learn more about the internal density distribution of the planet, which is a hot topic in research right now. So measuring apsidal precession or orbital decay are both very interesting prospects. And so either way, we're happy. So I just threw a bunch of theory at you, so we're all on the same page. But in summary, the orbital decay of ultra-short period exoplanets can easily be detected in measured transit center times. I say easily because it's not a very complicated model. This quadratic model, it's not difficult to fit. There's no convergence issues. It's a great model. Yet the caveat is that we need to have a long enough baseline of data. And so when I started looking into orbital decay, I was really excited about it, super interested, read all of the papers. and realized that we really need so much data in order to see this. And it's not just about having a big gap between observations. We really need to fill in that whole curve, that whole baseline to see the trend. So that is where the Exoplanet Transit Database comes in. And obviously I don't need to introduce this to you guys, and we just heard that fantastic presentation with an update. So I'll skip straight to why I started using this data. I had heard about ETD before and submitted a couple of times in my undergrad under Stan Shattuck, who some of you might have met. Without Stan, I wouldn't be here today. So thanks, Stan. I don't think he's in this meeting, but at some point I'm going to send him an update and be like, my whole master's thesis is because of you. So thank you, Stan. But I happened to go back to the ETD when I was looking into decay, and I looked at the WASP-12 plot from the website, and I went, wow, look at that. You can see this curve in the data. This plot is automatically generated, wasn't tuned to looking, to studying this or making it look good or anything like that. And it just, you can see that curvature. So that was super exciting. And I thought, okay, what about the other systems? Could we take this massive archive of data that's already here and find evidence of some divergence from those linear trends so that we can prioritize these follow-up studies and have something to work with instead of just trying to predict what might be decaying and then putting a lot of effort into follow-up studies without knowing what you're getting into. So I started looking around and realized that there's a lot of plots where it looks like there's something going on, but it's hard to tell. And I realized that if the reference period that's used from like the discovery epoch or something was a little bit off, then there may look like an artificial increase or decrease in the period that's just coming from that offset that we start with. I think that's what's going on, because there will be certain ones, like some of these ones in here, you could say maybe there's a bit of a trend there that something's going down. But then when we look at the data, it's actually linear. So if you do a best fit linear model, it will be a constant period preferred. Sorry, I bungled that a little bit. It's 7 a.m. for me, so it made sense in my brain, but not sure if it came out quite right. But basically, what I realized is that we really need to do a blind analysis of these targets from the ETD. We need to pull this data. We need to just scan through and try to pull out ones that are decaying without looking at all of the individual OC plots. So because we're looking for a lot of data, due to the high variance in the data, we have power in numbers for trying to find these trends. So we required that we had at least 80 observations with a data quality index of 1 to 3. So we automatically excluded 4 and 5 as an initial data cleaning measure, but there were still 30 systems that came out with this requirement. So we have the 30 systems there. I know that table's kind of a lot to look at, and it's not in alphabetical order, but I'll come back to it in a moment. The point is that we took 4,792 transit center times from the Exoplanet Transit Database. And so we just took those directly. Again, we did not look at the light curves. We did not refit the light curves. We did not double check the timestamps. We were just going, okay, what is an efficient way for us to find good candidates for follow-up studies? So we just scan this all at face value and see what we get. So for the model fitting approach, I wanted to approach this carefully because there is high variance in the data, and at times it seems that some of the error bars on the transit centers might be a little underestimated. So you'll see a trend, but they don't line up with the error bars. So we wanted to approach this carefully and developed this custom Metropolis Hastings MCMC routine that fits our 3 timing models that I introduced. And what I did is integrated it into this iterative sigma clipping algorithm so that we could remove spurious data points automatically without having to go in and pick them out, but then also without overdoing it and either accidentally introducing a trend that's not there or wiping something out that was there but just subtle. So we did this blind analysis of all 30 systems. Basically, I downloaded the data and then I didn't look at it again for this first round. I mean, I had done some experimenting to develop the code, clearly, And certain targets were popping out at me already just from that. But then what we did is we just went back and did this blind scan. And then we did a secondary analysis of the top 10 targets of interest from that blind analysis. And so what that involved is a little bit more work into cleaning up the data. So we went back and we looked at the pictures of the light curves to remove partial transits. We want a well-defined ingress and egress, and also removed any duplicate entries, and then double-checked the literature observations to make sure the timestamps had been converted from heliocentric or barycentric Julian days to heliocentric, just because those literature observations have such small eccentricities that if those are a bit off, it anchors the trend in the wrong spot. And so we did this kind of next step for these 10 targets just to clean things up a little bit more. But again, we didn't go in and actually pull any of the light curves. So you might notice that there's 8 targets there, and I said top 10. We also included WASP-4 and WASP-43 because those are highly relevant in the literature, and there's been a lot of back and forth studies on those planets. So we wanted to see what does the ETD data tell us about those. So here's our analysis of WASP-12b. So we found that it is decaying at a rate of minus 34 milliseconds per year. So it's a bit higher than some of the literature measurements, but given the relative uncertainties, it either agrees with a lot of them or is compatible with them. So this decay rate is perfectly reasonable. We're really excited about it because it's compatible with the literature. And not only that, but we did some model comparison using the Bayesian information criterion, which is essentially the chi-square statistic, but you add a penalty for the number of free parameters in a model. So we compared the BICs, expecting that a lower value means a better fit, and found that for WASP-12, the orbital decay model is the best fit. So our analysis of WASP-12b showed that we can retrieve the correct decay rate and have the correct interpretation of the different timing models given the comprehensive literature study that's been done. And you can also see those data points that were automatically removed by the algorithm that we developed. So that meant that our blind analysis is working pretty well because we can remove these extra data points that, you know, anyone would look at that and say, okay, those ones aren't going to fit in this trend, and so something must have happened. Those are automatically being removed, but we're not removing ones that would possibly drive the fit in a direction that it shouldn't go. So in total, we've identified 8 systems on the ETD that exhibit strong evidence of a statistically significant quadratic transit timing trend. And so for the purposes of this study, we interpret that as orbital decay because the apsidal precession model was not a better fit in any of our scenarios, but we did not pursue in more depth other possible sources of a departure from the linear ephemeris. So that is where we will be doing the follow-up studies. That would be very important. So we have this is a table from the paper that we're preparing. So we've got our targets here, and by no means is this a declaration that we have discovered new decaying planets. This is a prioritization for follow-up studies. Something that I noticed is that in the literature, there were attempts to make predictions about which planets would be decaying, and oftentimes they weren't really coming to fruition. Like there would be a prediction that seems good, and that planet seems to not be doing anything. So the purpose of this study was to take this data that already exists and see if there's any statistically significant trends so that we can follow up these planets in a more efficient way. So you probably want to see some plots. So I have a set of examples here. Have TRES-1, Hagey 19, WASP-4, and WASP-10. So the curvature is subtle, but the numbers don't lie. It appears to be there, and I approached this with trying to find every possible way that I could kill these as a candidate, you know, trying to make sure that there's no specific light curve that's driving the fits. But here we have some very strong evidence of a departure from the constant period model. So that's very exciting. And so for future work, we want to do follow-up studies. So the purpose of this study was to just have a base to jump off of, because we want to jump straight into studying these planets, but we need to have something that's already been done to set that baseline. So now we get to move into finding all possible, sources of data, combining everything together, getting new observations, maybe even some RV data if it exists. We can look at line of sight acceleration of the system, stuff like that. So, but a huge part is going to be new observations, and that is where the citizen science community absolutely is so important. We want to include co-authorship for any transits that are used in these follow-up studies, because for these we will really be refitting the light curves, doing a homogeneous analysis, contacting observers, and chasing every single person down until we get credit for all of the transits. And so some of you might have already heard that we're doing TRESS 1B first, and I have a little update on that because I think there was just a bit of a lack of communication on our side, so I apologize for that. And we'll be planning to do WASP 10B next year because we've applied for some space-based data, and we're going to wait and hope that works out. So for TRESS 1, this is a very preliminary plot. I think I don't even have the most updated list. This is the problem when I try to prepare a presentation when people are on vacation. I'm not sure where the most updated list is. It's not on my computer, but Billy has it. So this is a very preliminary result, but what we found is that after getting more observations from the citizen science community, the evidence of decay is even stronger, which is super exciting. And so this paper got pushed back because we wanted to do this general overview, and then I'm working on my master's, so things have been a bit slow. So now we're in another observing cycle of TRESS 1, so we thought let's just wait till the end of this one and then utilize all of that data. So I think it's still observable for a few more months in the Northern Hemisphere. I should have looked that up, but I can't quite remember. So if you want to take some transits, if we can have a full transit, we'll use it and give full credit and everything. So I just wanted to point out that that big chunk of data at the end, that is what happened when we asked for observations. We didn't even necessarily make a huge call. We just started sending a couple of emails, and it's just steamrolled, and now we have this massive anchor in the baseline, which is so exciting. So thank you so much for that. And we will be continuing this work, and I'm happy to talk about it more. And after that, I don't want to bore you for too long. I just wanted to thank all of you. I mean, I'm completely indebted to the work that you do. This would not be possible, and I am constantly amazed at the skill and dedication of the ETD observers. And I left my email there, so you can contact me if you're interested in chatting. I'm happy to answer questions, and I'm super excited to work with you all more in the future. So thank you again for giving me a chance to talk here. This was perfect timing, and I'm really excited to share it with you today.